Welcome everyone to today's a16z crypto research seminar. Very pleased to welcome Brett Falk, who's a professor at the University of Pennsylvania. Did his grad work at UCLA, finished there 2010, working mostly on multiparty computation stuff,
Yep.
I guess, MPC, yeah. So he works on lots of different parts of the blockchain space, including some stuff that is near and dear to many of our hearts, which is voting, which is what we're going to talk about today. So Brett, it's all
Thanks.
yours. Yep.
Thanks for the intro. I'm glad to be here. So just as I haven't met most of you, so here's the slightly longer background. It's like I got into cryptography mostly in secure multi-party computation and thinking about like practical applications of secure multi-party computation. We did some stuff on, trying to calculate the probability satellites are going to collide without revealing the underlying data. And now in the MPC space, I do a lot of stuff on distributed oblivious RAM. So how can you do secure computation in a RAM-based model as opposed to a circuit-based model? But I've also been doing for the last bunch of years now, like more and more blockchain stuff. I teach the blockchain course for Penn's MCIT online program for the last 8 or 9 semesters, I think, and been doing some stuff on stablecoins with people at the Stevens Center for Innovation in Finance, looking at NFT royalties. We've been doing some modeling of trading fees and AMMs. On the crypto side, I've been really interested in using threshold signature schemes. It's like kind of a cool application of MPC. But today I want to just talk about this thing, on-chain governance. So this is not exactly my area, but it's something I think is really interesting. And so I'll keep this sort of at a pretty high level. Hopefully this should be like a fun talk and not too like technically deep, but there's like lots of papers behind it that we can talk about later if you want. So this is in 2 parts. First, governance to elect block producers for consensus committees, and second, DAO governance. And I think they're like useful to think about in a little bit different ways, and we've modeled them a little differently. So here's part 1. This is based on this paper with Jerry Tsoukalos, who's at BU, and Alon Benheim, who's now at Microsoft. But basically, the idea of this model is like there's a lot of proof-of-stake blockchain protocols where you elect a consensus committee, and then once that committee is elected, they run some classical consensus algorithm. And for the purpose of this talk, we don't really care what that consensus algorithm is. We just sort of care, how do you choose this committee in a way that's good for you? And from a cryptographic standpoint, the simplest notion of good for you is 2/3 honest, right? That's like the very simplest criteria you could consider, right? And these committee-based consensus is used in a lot of places, like it's the foundation of all the Cosmos chains, and so there are lots of Cosmos chains you've probably heard of, right, and are familiar with, and it's also for other chains like Tron and EOS, and so it's used a lot. And one of the main advantages is that these chains, right, get instant finality, right? So if you have Nakamoto consensus, you have a longest chain rule, right? You can have chain splits, and before the merge, Ethereum had like 300 uncles per day. Bitcoin has only about 1 uncle per month, but there's still an issue of finality. It makes bridging hard, it makes a lot of things hard. Whereas most committee-based consensus chains, right, advertise instant finality. And what this means is that basically that they assume that the elected committee will be honest every single time, and then you can claim instant finality, and then you get no forks. So this is sort of a nice thing. One other thing that I kind of like about committee-based consensus is you can then, if you have like a kind of small semi-static committee, you can do kind of interesting stuff. You can ask the committee to do other stuff for you. So like you can have a secret mempool because the committee members are all running Intel SGX, like the secret network. You can ask the committee members to do things like a distributed key generation, like Osmosis has been talking about doing this kind of thing. You can ask the committee members to hold shares of a secret. So Algorand Research had this like stuff on, can a public blockchain keep a secret by secret sharing to committee members. You can have the committee members be price oracles. So Terra did this before they collapsed. It's sort of an interesting kind of thing. If you need price oracles as part of your chain, you just ask them to do this. You can elect block producers for other chains. The Binance chain does this for BNB. You can build bridges like this, right? A lot of this is like a nice architecture for a lot of cross-chain bridges. So like Thorchain, Axelar, Zeta Chain, these are all Cosmos chains where the committee members also run validators right on these other chains so they can manage liquidity pools or bridge contracts. So it's kind of like an interesting, like something that's nice that you can do with these like committee-based consensus protocols. So it's sort of a reason why we might want to think about using them. Right, the big problem with them is that they tend to be kind of small and stagnant, right? The consensus protocol means that you can't have a really big committee. And so these committees are kind of small, and they don't change that much. Even if you have elections a lot, the committee is like pretty stagnant. And so that's kind of a problem compared to, like a proof of work chain, for example. Like they have a lot more leader rotation. But assuming we are going to think about committee-based consensus, the question is like, how do we elect a committee? That's like what I want to talk about here. You have one question is, sort of what is the Sybil resistance mechanism? How do you identify committee members and voters? This can be proof of stake, it can be proof of work. Most people think of the proof of stake model, but it has been proposed that you could run Cosmos on top of proof of work if you wanted to and just run Tendermint at an elected committee. There is an early paper, Bizcoin, which basically said you can have like a hash-based Byzantine agreement protocol on top of Bitcoin to get some finality. But then once you have the proof of stake, once you have the mechanism for identifying who's a voter and how much their vote weight is, the question is like, how do you aggregate votes? The Cosmos chains basically all use a single vote. Like you get a vote and it's proportional to your stake, but like as an address, you get one vote. You could have approval voting, where you can approve of any number of people. EOS does this, and Telos does this, and whatever you think about EOS, it's still an interesting voting mechanism. And you could have a lottery-based system, and this. Well, so there's lots of different ways you can kind of think about this. So I want to talk about sort of like how does this system work in terms of mostly on approval voting, because that's kind of the interesting thing here. So what's the best way to choose this committee, and how does approval voting play into this? But we'll start as a warm-up with the lottery-based system, because this is kind of the easiest to analyze. And so like if you look at the Algorand paper, they make an assumption. They say 80% of the stake is honest, and the classical consensus protocol will succeed if 2/3 of the committee is honest. And now you have a concentration bound, right? What's the probability that a binomial is, with a binomial with parameter 0.8 is below 2/3, right? It's very small, and they suggest in some of their parameters that you want to choose this so that this probability is below either like 10 to the minus 12 or 10 to the minus 18. And if you want to claim instant finality, you want to say that you'll never, ever have a bad committee. And so they say if the failure probability is 10 to the minus 12, then, and you elect a new committee every 4 seconds, then you can have a failure time of, on average, 120,000.
Do they have any resilience against bad committees, or are they just dead?
In the original, so I can't speak to exactly what their code is doing now, but in the basic, in the original paper, I think there's no resilience. You just have to say that.
There have been versions where they had like a sort of emergency backup procedure where if there's a fork, the next committee votes on which branch of the fork to extend. I don't know what actually got deployed, but
Doesn't the committee at time t pick the committee, or have a huge amount of influence on the committee at time t, like pick the randomness?
Okay, so there's a big question, right? How do you, if you were going to do a lottery, doing the randomness, right, is obviously really hard, right? That's sort of not the purpose of this talk, right? Algorand, right, they're using verifiable random functions, and so you have some control over that, but not very much, right? So there's like a seed that goes into the VRF, right? In the next committee, everybody generates their own VRF output, right? And then you choose the lowest bunch of them. It seems that there's not that much you can, even if you're the current committee, right? You get to choose a little bit, but like it doesn't. You don't have that much control, right? There's other things you can do, right? Ethereum also does something kind of like this, right? And they have RANDAO where it's a commit reveal scheme, right? And so you can ask questions about like, what is the randomness going into this lottery-based mechanism? I was just putting this up sort of as a baseline thing of if you're thinking about honest committees, like here's kind of the analysis that would come up like in the original Algorand paper, right? And you can just say, you have a turn-off bound, and so if your stake percentage, if your percentage of honest stake is above your threshold, right, then as the number of tokens goes to infinity, then your chance of an honest committee goes to 1, exponentially quickly. in like some of the stuff, Silvio's sort of said like we like lottery because there's no mechanisms behind it, right? Like it's hard to design a good mechanism. It's sort of like the simplest kind of thing where there's less that can go wrong. Like there's no rewards for block producers, there's no slashing, there's no voting, and maybe this is a good thing. We're going to be talking about when there is voting, but this is sort of the baseline. Ethereum, after the merge, right, does the same kind of thing where for finality. So I didn't quite put them in the committee-based consensus model because their consensus is sort of split here, but the finality gadget, right, chooses a committee every epoch, and they do a similar kind of analysis with different numbers. They assume 2/3 of the stake is honest, and then they analyze the probability that more than 1/3 of the committee will be dishonest. So you again get this Chernoff bound that gives you something nice. They also, they choose their committee size to have a 2 to the minus 40 probability, which is basically the same as 10 to the minus 12, which is what Algorand shows. And so sort of looking around where these things came from, there's like an old, like Vitalik had thrown out some numbers of saying, we think 2/3 and 1/3 and 2 to the minus 40, and that seems to have been how these numbers were chosen. And then now there's 128 committee members, because if you do this binomial probability, you get 111 you need, and you round it up to a power of 2, and you get 128. And so there's a little bit of arbitrariness in sort of how these things are chosen, but this is the analysis that kind of backs them as far as I can tell.
So I agree, some of the parameters are arbitrary. The 2/3 I would not have thought. Or you mean you don't want it to go more than 2/3 malicious?
Yeah, yeah. You have to assume 2/3 of the stake is honest to get the 1/3. So right there's for them they want a probability that no more than 1/3 of the committee is malicious, right? And whereas Algorand wanted the probability that no more than one. Here they want no more than 2/3 of the committee is malicious, and Algorand wanted no more than 1/3 of the committee is malicious. But then this question of how much of the stake is honest, you need to assume more of the stake is honest than your threshold, right? Algorand assumes 0.8 because that's more than 2/3, and here they assume 2/3 because that's more than 1/3.
Here my guess would be like 2/3 honest stake seems necessary to have kind of reliable liveness.
Okay, yeah, sure. So maybe you just start with that.
That assumption you inherit from other things.
Okay, yeah.
And then you also, like, more than 2/3 malicious also seems like a bad threshold to cross.
Yeah.
And maybe a more. So these I think are a little less arbitrary.
Okay.
1/3, 2/3.
So, right, the lottery-based committee consensus like works well in these analyses if the committee is large enough and the supermajority of the stake is honest. And the question is sort of, can you do something better with voting if you allow people to vote? So we made a model that was just trying to capture what was done in the past here, which is you have a really dichotomous outcome. You win if 2/3 of the committee is honest, and you lose if more than 1/3, or you can choose whatever parameter, some alpha fraction, whatever is your the tolerance in your consensus protocol. But for now, you think you win if you can elect a committee with 2/3 honest people, and you lose if more than that, if less than 2/3 is honest. We assume that all the voters, their goal is to create an honest committee. They just don't really know who's honest or not. You have very little information in these systems when you're electing somebody to be on the committee. And for this model, we kind of ignore like secondary characteristics of who you might want in a committee, of like whether they're extracting MEV or whether they have really low latency or something like that. Just as like a first step, we want to say like, can we recreate the lottery analysis with some voting? And we're going to start with approval voting because I think this is the sort of most general that's been used, right? There are lots of voting schemes, and we'll talk about some of them later, but like people have actually been using approval voting to elect consensus. And here the idea of approval voting is you don't get to vote for one person, you get to approve of up to K candidates, and they all get your full vote weight, right? It's not, your vote is not split between them. If you vote for 3, they all get your full approval, and then you count, the committee is made up of the people who get the most approvals. And in a single vote system like in Cosmos, you get one candidate. So this could be like one approval voting. You get only one person you can vote for. And the problem with approval voting is basically that it's kind of complicated for the voters. Even even if voters are not assumed to be strategic, like even if you're an honest voter, there's not an obvious sort of honest strategy, right? Like if I think the candidates are from best to worst, like A, B, C, D, or actually here, I guess in this example, I think they're best to worst in B, A, D, C, right? Do I vote for just the best, or do I vote for the 2 best, or the 3 best, or the 4 best? Like it's not actually obvious. Like there's no heuristic for voters, right? Like voters kind of have to be strategic almost. Because of the way that the system is set up. Whereas normally, like for a single vote election, you can be, if you're sort of a myopic or a not strategic voter, like it's kind of obvious, you vote for the person you like best, right?
So K here is chosen by the voter, or K is voted by the...
Okay, so sorry. So in terms of how many people you are allowed to vote for, so in EOS, they just cap it at 30. In this, normally we assume that you can vote for up to, okay, right? You don't have to vote for this. You get to choose how many people you vote for up to some threshold, or maybe there's no threshold, right? You can vote for everybody if you wanted to. So we'll focus mostly on when people are voting for fairly small numbers. But you can, for your thoughts, you can think of like K equals 30. You can vote for up to 30 people, say, and that makes sense when the committee is for EOS of size 21. But
I was asking because if K is like small, you can almost. It's cheating a little bit, but you can almost say what I mean by honest strategy is that you actually vote for a full K people.
Yeah, you would always vote for that many people.
But for 30, that's sort of unreasonable.
Yeah. So that's right. You could say, and we'll look at this a little bit. We'll do some simulations and stuff where basically we say, like, suppose everybody just votes for their top 2, or everybody votes for the top 3, and the sort of punchline is that actually does really pretty well, even though that's not the optimal strategy. Yeah.
So when you say the votes have preference, like B, A, C, D, or whatever, you're saying that the votes have like different priors over which candidates are most likely
so
to be.
here's the little bit of this model. We assume there's M candidates, and M is known. Every candidate for the committee is probability with some, is honest with probability P and dishonest with probability 1 minus P. So there's 2 types of candidates, good and bad candidates. You have N voters, and every voter receives a signal about the candidate's type, and this allows them to calculate a posterior that candidate is honest.
In practice, that signal is past behavior, not current round behavior.
Yeah, I mean, it could be past behavior. It could be like what you heard about them on Twitter. It could be, I mean, so we assume it's a very noisy signal, right? But you have some information about the candidate, and these signals, Then the question is sort of how does this voting work as an information aggregation mechanism? Like, is it good at sort of crowdsourcing the weak signals that people get? So my intuition when we started this, I thought, yeah.
So what's the information structure? Like, are you assuming the signals are IID conditional on type? Or
The signals are IID conditional on type.
Okay.
So and I sort of thought there was like a simple thing would be maybe like, if you want 2/3 of the committee to be honest, you vote for people who you think have a 2/3 chance of being honest. Like I thought there would be some kind of simple thing like this, and you could solve it in like an hour, and it would be fun. So we would call this like a threshold voting strategy, where you basically vote for everybody who you think is above some threshold tau of being honest. And if you do this, then you can analyze things reasonably nicely because the signals are IID conditioned on type. Then the number of votes, if everybody follows a strategy like this, the number of votes each candidate gets is independent conditioned on type, and it's a Poisson binomial, right? Where it's not like a regular binomial because you might have different voters vote for you with different probabilities because the different voters might have different precisions. So it's like you're adding up a bunch of 0 1s with different probabilities, but they're independent because these signals are independent. So we get a Poisson binomial. The number of votes for a malicious producer or malicious candidate is also a Poisson binomial with different parameters. And now you're going to get some separation. And now the chance that you have an honest committee is a little bit messy because now you have to say, what's the probability that the person, if the committee is of size K, what's the probability that the 2/3 Kth sample from this distribution is above the 1/3 Kth sample from this other distribution? You can get kind of messy sums for doing this, and you can actually solve this out. And so you can get some analytic bounds on this when people behave like this. And so here, if you have one voter and you set some parameters and you do this, you get actually, like, if the voter says, I'm going to vote for everybody who's more than, like, 0.2 honest, this is not good. This is like where you think, here I'm voting for everybody who's at least like has a 0.6 chance of being honest. So this almost looks good. There's like a spike that's like around 2/3. Turns out it's not at 2/3. In this example, it's like at 74%. And basically what's happening here is, here your threshold is too low. You're kind of voting for everybody and you have no distinguishing ability. And here you're voting for nobody and you have no distinguishing ability, and there's some way where you can start to distinguish. So that's look good. If you have two voters though, it's bad. All of a sudden things get totally messy because now every candidate gets 0, 1, or 2 votes. Here, your threshold's too low, everybody gets 2 votes. And then you move the threshold up if both voters follow the same threshold. Then here, the good candidates get 2 votes, the bad candidates get 1 vote. And then you move it a little bit and they both get 1 vote. And then here, the good candidates get 1 and the bad get 0. And then here they both get 0. And so it's kind of a mess. Right? Like even with 2 voters, like there's not like some clean strategy of like vote for 2/3 honest, like I was hoping. And 3 voters, you get 3 peaks, and it's it's bad. But once you get a lot of voters, right, the central limit theorem kicks in, and or basically you have concentration bounds, and everything is kind of fine, whatever anybody does. And so as long as everybody follows a threshold sort of in the middle, it all works pretty well. But there's not like this clean sort of thing that I was hoping for when I started this. And so the question is like, how should you choose this optimal threshold if you were going to try to be a voter? Like, how should you think about this? And what value maximizes the committee? This is actually like really complicated because it depends on the number of voters a lot in like this complicated way. But once you have a lot of voters, things are generally okay. But if you think about it for a minute, this isn't the only kind of strategy. Like another type of strategy is basically don't have some threshold, but instead vote for like the top 3 people you think are best. Like that's actually like a different class of strategy than vote for everybody you think is like a 75% chance of honest. And even these 2 strategies, you can have more complicated strategies, but like these 2 are sort of the ones we focused on because they seem kind of the most natural. In this cardinal voting strategy, you just vote for the top like kappa candidates in our thing. And then you get single choice voting if you vote for the top 1 candidate. So it's sort of like a generalization of single choice voting. The problem here is that now who you vote for is not independent anymore. And so you can't get any kind of analysis. It's a mess. Because if somebody is at the top, they push somebody else out of the top. But you can do some kind of simulations. Well, actually, even before this, in EOS, we scraped all the votes from EOS, and it does seem like people are kind of doing this. The committee size is 21, and so this is the fraction of the stake and how many people they voted for, right? So the limit is 30, so a lot of people just max out their votes and just vote for 30.
Are these proprietary clients? Is this open source clients, or is this
There's only like one client. I mean, like when you say client, the client, you mean the node. So, I mean, they're private companies running these nodes. I think they're all running the same software client. I mean, so this, you can take this with a grain of salt in terms of, but this is sort of the approval voting data we can get because Cosmos doesn't do approval voting. So, but it's just sort of interesting to see this huge spike at 21. Like a lot of people seem to have this heuristic, which is if you want a 21-person committee, you vote for 21 people. And that heuristic actually works when you're the single voter. So if you only have 1 voter, you can show that this voting for, and you want a committee of size k, voting for k people is optimal, and you get the best thing. So here's how many people like you vote for. If you vote for 10, it's not good, but if you vote for like 21, that's the best, and it gets worse as you go down because you get less discrimination. And just for reference, here's this single voter threshold thing that you can never get as high following the threshold strategy as you can just voting for the 21 best.
So optimal here could mean a couple of different things.
Yeah.
So first, I assume you mean probability.
Probability of honest committee.
Okay, but even then, like, is it conditional on signals? Optimals, like beta?
No. So this is right. Because if you can condition on signals, right, you can have now an even sort of broader class of. So right, I was saying like we focused on these like two really simple types of strategies, which we called like threshold and cardinal. Do you vote for everybody with this probability more, or the top 21 or something? But you could imagine saying like something that the strategy is like much more complicated depending on the exact signals you get. If there's a gap between signals, then you do something. Right, those strategies get even crazier. So you might be able to do something. So this is optimal in the sense of if you assume your strategy, you have to fix your strategy before you see the realization of your signals. And then you can now ask this question of like, well, if people are going to follow a kind of cardinal strategy and maybe a suboptimal one, but how does it work if you ask people how many people they're going to vote for? And it actually gets better. So if everybody votes for just their top choice, you get this. This is the success probability for some low parameters. So this is like single choice voting. If everybody votes for the top two, you do a little better. If you top three, you do a little better. Top four, you do a little better. And it seems to get it's increasing for a while. So basically, like even if people follow a suboptimal kind of strategy, they just follow these heuristics, like I'm going to vote for the top 5 people, you do much better than if you just say everybody votes for the top 1 person. And in this really idealized model where everybody's incentives are aligned, and so the voters are giving you some information, you do obviously better than a lottery, because in the lottery it's just random, right? In this model, and so the lottery is this fixed line because you don't get to vote for anybody.
But a lottery where we remove, sorry about that, a lottery where we remove the bad people, like according to some strategy, might be better.
Yeah, maybe.
Okay.
Yeah, and I mean, this is again, we're thinking of the single shot analysis because like this was, right, all the like Algorand paper considers the single shot analysis. You say we want the probability, we don't consider even repeated elections, right, because we just want the probability to be so low that if we take a union bound over every election we're ever going to do, the probability will still be small, right? But yeah, there's then all kinds of interesting stuff if you could now say we're going to do repeated elections, and now you can penalize people, right? And you get all kinds of sort of more interesting mechanisms, basically. But yeah, this doesn't really incorporate that at this point. But in these things, like all the methods converge sort of exponentially quickly in the number of voters, and the optimal strategy is super hard, but the kind of interesting take home for me was that like the approval voting seemed to really help in this information aggregation here in terms of getting this committee, that like even though you can't find an optimal strategy, just like having everybody vote for 2 people like actually does better, which is.
So you just mean the graph on the previous slide, right? Okay.
Are you going to talk about protocols for it, or are we, just in terms of the bandwidth, Rho is going to pay an extra n factor to do this?
Yeah, so no, we didn't consider that at all in terms of, but I don't think that's a big thing in terms of, well, okay, so in terms of the protocols, right, so the way a lot of these things are set up, right, you vote, and so one reason these things stagnate is, right, you vote by like locking in a contract, and you can move your votes at any time, so it's sort of continuous voting, but then you're not sending around these votes, it's not like you're sending around these votes all the time. Yeah.
Do you have a notion of the max possible in this setting if you actually had one party get everybody's signal and aggregate them?
Yeah, I mean, so that's basically going to be the best, and that's
like where would it be on this graph, I guess, is the question.
Yeah, so that's basically the single voter setting. So if you basically just say, in this setting where everybody's incentives are aligned, the best thing you could do is just everybody give me your signal. I will calculate the posterior based on that, and then I will do the one vote for everybody. And then the best thing you can do is to vote for the 21 people you want, if you can aggregate.
I guess I'm just wondering, like, where it would fit on this graph, like what would the actual success probability be?
Oh, okay. So, I mean, this number requires, like, to get a graph where we had to set a bunch of sort of random parameters, like what's the a priori probability that a candidate is honest, and what is the variance of their signal, the voter signals and stuff. So in terms of like how high it would get, that basically, you're right, actually, for these parameters, I don't have that on this graph, and that's a good question. Yeah, so I put it on the other graph, but I don't have it on this graph, so I don't know what it would be off the top of my head, because.
Do you have a sense, though? I mean, because it kind of looks like the approval voting. It looks like
yeah.
It's hitting an asymptote.
Yeah, I think. It certainly can't always get better, right? Like at some point, it's got to go back down because you're kind of losing information. If you approve of every candidate in the space, so again, this also depends on there's some fixed known number of candidates, and once you get close to approving of everybody, you lose any power of discrimination, right? But yeah, that's an interesting question. I don't know. And so there's like a bunch of other questions you can ask about this. We started looking, we have a recent paper on using quadratic voting as an information aggregation mechanism, but there's other types of voting. You can have kind of ranked choice voting. Quadratic voting is kind of even orthogonal to approval voting. You could have quadratic approval voting, because quadratic is just like how you weight your stake. You can imagine this model is like very simple right now, right? It's just everybody's honest, but if you have some malicious voters, right, what fraction of malicious voters can you tolerate? You could sort of try to optimize for a committee that has some secondary features like performance or something. You could imagine vote buying in these systems. And so there's a lot of kind of interesting things here, but our first step was to try to move these analyses of the lottery mechanism into a system where there's voting, because like a lot of these committee-based consensus have interesting voting mechanisms. Okay, so that was what we're thinking about in terms of like electing blockchain committees. But then there's a second kind of voting. I mean, there's lots of kinds of voting, but the second thing I want to talk about is sort of DAO governance. And it seems like the voting models here are like pretty different in terms of how you think about token-weighted voting in the DAO context. So we're going to switch gears a little bit. We'll still talk about approval voting because approval voting still comes into these systems. And this is more work in progress, so I won't have like as clean results. But let's talk about sort of DAO governance. So like Compound sort of started a lot of the DAO governance hype in 2020, and they introduced governance at the beginning of DeFi summer, and this was lots of fun. And then lots of people kind of forked Compound's governance, either like directly forking their contracts or essentially like taking their model. And their model is what gets called like initiative voting or sometimes amendment voting. And the way it works is like voters make yes or no proposals. You need to have some threshold. So like in Uniswap, you need like 1% of the tokens to be able to make a proposal. And for Compound, you need 25,000 comp tokens to make a proposal. And then all the voters have some window of time to vote yes, no on this proposal. And if it gets a majority in that time, then it passes, otherwise it fails. And the time windows seem to be about 3 days. There's lots of sort of similarities in how these systems are done. We scraped all the votes from Uniswap, Compound, Lido, and Aave, and Maker. And so if you separate from this talk, if you're interested in like actual voting behavior, we have that too. But then the outlier here is Maker. Maker went and did their own thing, which they call continuous voting. And we'll talk about that in a little bit, but basically there is no time window and you can just vote for any proposal that's ever been made. And that kind of thing makes sense in this model where what we're going to talk about is the proposals are mutually exclusive, right? So anytime some proposal comes up, it's mutually exclusive. You can only be in the state of one proposal. And this is like why it's called like an amendment voting. You're like amending the laws, but there's like only one set of laws. And this makes sense for like a lot of blockchain votes where like you're setting the fees for like on Uniswap or something, you're setting the loan to value ratio on Aave or something. There can be like only one loan to value ratio. And somebody might say it's like 60%. Somebody can make a proposal to make it 70%, but you can't have both, right? There's just one parameter here. Or like the liquidation threshold, how low does your collateral have to go before you're liquidated? There's like one parameter here, or one parameter per collateral asset. But these are mutually exclusive, right? Some DeFi votes, right, are not mutually exclusive. Like, do we deploy to this layer 2 or that layer 2? You could do both. This analysis doesn't really capture that, and like the continuous voting model doesn't address that at all. So just as we talk about the rest of it, we're thinking of the mutually exclusive votes here. Yep.
Just to clarify, you think about binary votes, right? Not
yeah.
like
So
voting on the like continuous.
So you can think of a continuous kind of thing. You might be voting on something continuous, like what the fees should be, but the voting mechanism, like what Compound has set up, is only binary votes. So if you want the fee to be 3% or 0.3%, right, somebody needs to make that proposal, and then you get to vote yes, no. And if you want it to be 0.35%, somebody needs to make that proposal. So it's an interesting question, and actually we have another paper on looking at essentially like where the votes are continuous. So imagine you want to set a fee, and it's from a continuous space like 0, 1, and voters get to propose like what they want the fee to be, and then you do stake-weighted aggregation to find the fee, right? How does that do as an information discovery mechanism? So again, like I like these models where voters have imperfect information, like nobody knows what would be the best fee to, you know, maximize the profits for uni holders, right? But we assume their incentives are aligned. They all have they have different amounts of information, right? You'd like to sort of crowdsource from these people or something. So you can ask this question where voters are allowed to make a continuous vote. We have a paper on that. I'm not going to talk about it much here, but I'm happy to talk to you after. It's a really interesting model. But that's, right, it's an interesting question to me, like why doesn't Compound do that, right? Compound could have done that, right, but they don't. And again, it only works for some things, like continuous voting doesn't work of like, do I deploy to Arbitrum or not? But like, but for fees and stuff, which is a big part of a lot of this, or, you know, loan to value, like system parameters in general, like it's a really interesting question. Why not allow people to vote continuously? In there, not continuously like in time, but you know, have continuous voting space. So when I started thinking about this, I wanted to like see who's like written about this, and I found this paper that was like, and analyzing crypto initiative voting. And I was like, great, somebody already did this, like I don't need to do it. And like, it turns out it was written in 2004, analyzing exactly this voting mechanism on crypto initiatives. And I was like, how is this possible? So this is, I was very funny, but so they model this exact kind of thing for initiative voting or amendment voting. And here's what they mean by crypto initiatives. And I want to go through this example because it's a fun example. And they say, suppose you have something, there are 3 proposals, and there are 3 voters, okay? And we say Q is the status quo. So this is like we're starting things out. The initial fee is 0.03%, and somebody wants to make a proposal A to like 0.05%, and somebody makes a proposal B to 0.07% or something. And here's the voters. There's no uncertainty. The voters know what they want. And so initiative voting says, first, if we vote A against Q, somebody proposes A wins 2 to 1. Somebody proposes B. Now the status quo is A, right? And A still wins over B, right? And so the final outcome is A, right? So this is like how initiative voting works. But voter 1 is unhappy here. Voter 1 wanted B. So what does voter 1 do? Voter 1 introduces what they call a crypto initiative, and that's where this crypto initiative came in, right? Which is they say voter 1 can introduce a new initiative, and voter 1 introduces this new option X. And now what happens, right? If the votes are in the order A, X, B, right? A beats Q like it did last time, but now X beats A 2 to 1.
How did XJ jump ahead into the second position?
So which?
Oh, they can just put it in the second position.
Yeah, so they get to choose. You're a malicious party. You craft an initiative that you look at the 3 voters, right? You can choose your own preference of ordering of it, and you just choose it. So you craft an initiative so that voter 2 hates it and voter 3 loves it. And maybe depending on the voters, that's not possible. But assume for a second that you have that control, right? And then in the 3rd round of voting, B beats X, and B is chosen. So by introducing this crypto initiative, which you didn't want, voter 1 actually gets to move from A to B and they get to make themselves happier, right? And so the point of that paper was to say, like, this mechanism is really vulnerable to this kind of attacks of people introducing initiatives that they don't want. And another thing you can notice from this graph, right, is that the outcome is also not Pareto optimal, right? Like everybody would have procured Q to B, but B was still chosen, right? This is bad. And so this is sort of like classical stuff that was sort of new to me, but it's classical in the voting literature. And there's like a really nice way to think about this, which is in terms of...
Explain why it's called the crypto initiative?
Oh, they called a crypto initiative because it's like a secret kind of initiative that is put in there for your secret, like your malicious goal of making BU win here. But that was the only thing. There was no, cryptocurrency.
Byzantine initiative.
Yeah, I guess maybe more.
Yeah.
But yeah, when you search for cryptography and initiative voting or crypto initiative voting, this comes up and it's great. And I was like, it's perfect. It's exactly the model.
I feel like this is conflating 2 different things, right? One is just like the specific voting procedure you're using, right? And so like round-based procedures have lots of problems, basically.
Yeah, exactly.
The other thing is this kind of, insert
Yeah.
an extra initiative.
That's right.
And
But
so,
basically,
so more satisfying would be like extra initiatives screw up all ways you might do voting. That
yeah.
would be
But the extra initiatives are much easier to screw up the round-based thing, right? Extra initiatives, right, are not going to where everybody's preferences are fixed and known, right? And they're not going to screw up plurality voting, really. Actually, that's not true. They can screw up plurality voting too. But so yeah, that's an interesting question.
So I guess you're saying that if you look at Compound, Uniswap, et cetera, they're basically doing round-based voting, whether you like it or not.
Yeah, they are doing round-based voting. In terms of like thinking about round-based voting, there's this like really nice notion of this tournament graph where you just say you make a graph of all of the proposals and you have directed edges from which one would win in a head-to-head competition. And what basically this third initiative did is it puts in this X, which now makes this cycle, right? And now you can get anywhere, right? And this is like the Condorcet paradox, where even though everybody's preference orders are transitive, right, the final ordering is not transitive. And you can say that there's like this notion of like a Condorcet set where basically everything in the set is preferred to everything outside of the set, and it's the smallest set with this property, that in this initiative voting, then the outcome is always part of the Condorcet set, and anything in the Condorcet set can be reached. So like the outcome is very dependent on the ordering of the initiatives. And this is, yeah, again, potentially an issue with this like iterative type of voting.
Once you have Condorcet cycles, you're just in trouble, basically, right? So, and in particular, like the first part of that's actually that's a good thing. The first property, right?
That you always
so you
get to
want the
something.
winner to be part of that, and then I don't know. So it just feels like the extra initiatives would be bad for all.
Yeah.
Not only.
Yeah, no,
for this
that's actually, no, that's a really interesting question, right? Is like which ones are susceptible to adding extra initiatives and having the outcome be much worse.
Which presumably
right?
all of them.
Yeah.
I
It
guess.
has to be all of them.
I would think
Yeah.
so.
Yeah. So to sort of change things up, right? Maker does what they call continuous voting, and they can do this because they are in their executive votes, at least, are in this exclusive. They're the mutually exclusive because they're actually voting on a contract. They have the system parameters are set by a contract, and you just get to say, I want this address. This is the contract I want to hold the system current. It's like a list of variables, basically. And so you just vote on this list of variables. And these things are, for adding and removing collateral types and vault types and various system parameters. And as sort of an aside, if you've spent some time with MakerDAO, they made up bizarro names for everything they do. So we wanted to think about these kind of DAO governance, and the way I wanted to think about it was different than sort of the analysis we saw in terms of these classical analyses where everybody has a strict preference ordering. I want to say that like basically, again, people have imperfect information, but their preferences are mostly aligned. Like if you're voting for the loan to value ratio or what types of collateral for MakerDAO, we can, to a first approximation, I think, assume that all the Maker voters want Maker to succeed mostly, and they want to choose things that will benefit the protocol the most. It's just there's a lot of uncertainty of what should the loan to value ratio be to be the safest, or what should the collateral types, is it safe or not to use Bitcoin or WBTC as a collateral type. And so as like an example, like they have limited information. Here's an Aave proposal, and it's a proposal like this, adjust 14 total risk parameters. I'm pretty confident that like nobody who voted on that really had perfect information on what that meant, right? Even the people who proposed it did a bunch of simulations, right, as Chaos Lab, and they're probably pretty well informed, but they still don't know what's going to happen next year. So I think this model of having like weak information is really interesting. And so then the question is like, how does this kinds of like initiative voting or continuous voting or approval voting play into this question of information aggregation? So we have this model where basically every proposal has some unknown quality, like proposal Q has unknown quality QJ, and the voters receive some signal, which is some noisy signal about the quality, and then they have to choose which proposals to vote for. And Maker not only does continuous voting, it does continuous approval voting. So you can approve of a whole bunch of with the spells, but of contracts with the parameters, and the one with the most approvals wins. And so the question is kind of like, what what type of mechanism is best at crowdsourcing information here? It's kind of like the last one, but in now a different model. And we're thinking about like this kind of initiative or head-to-head voting. And then you can also ask questions about like malicious attack. So I have some like early results on this, and so I won't go too deep into this because we're just sort of finishing these things, or we're working on these now. So I don't know how easy this is to see here, but basically we said, suppose you, what is the expected quality? This is an example. You have 4 proposals. They have different qualities, and everybody gets a signal about these qualities. And the qualities are between 0 and 1. And what's the expected quality of the winner, right? Where the randomness is over the random signals people get. There's 3 cases for initiative voting because it depends on the ordering, right? Initiative voting is like very dependent on the ordering. So we say, imagine you have the best case ordering. That's this, this gray line or brown line, I guess, up at the top. If initiative voting, if you have the best case ordering, does really well. But you can focus on the red line is the random ordering. So if you just choose a random ordering of the initiatives, you do pretty well. Like once you have some voters, right, the probability, the expected quality of the proposal goes up to 1 really fast. And interestingly, it does better than this. This is plurality here. Again, these colors are hard to see here. But basically, plurality voting does worse at aggregating information than initiative voting in a random order, and it only crosses at the like worst order. Like if you say the worst if the maliciously ordered proposals can, for small numbers of voters, plurality voting does better. But plurality voting does badly. I was surprised about this in terms of crowdsourcing information. And then you can ask, well, what if you allow approval voting like Maker does? Does that do better at aggregating information here? And here, again, the approval voting is super hard to. The other things, right, in our model, it's sort of simple. You can get analytic closed form expressions and you can model everything. In approval voting, you have to simulate. But approval voting basically does worse. Like if everybody votes for their top 2, that actually does worse at information aggregation than either plurality, where everybody just votes for the 1, or even the random ordered initiative voting. So this is like, this was a surprise to me in terms of this information aggregation, that this initiative voting somehow is good for that. Yeah.
So here only one proposal wins, right?
Yeah, so here only one proposal wins.
Approval is kind of the case of having more votes than their outcomes. So
yeah,
suboptimal.
yeah. But it's basically a way of saying, like, I have limited information, right? Here are 2, right? So I'm a voter. There are 2 candidate proposals I both think are pretty good, right? And if I'm only allowed 1 vote, right, I may have to choose, and I kind of choose randomly between them. And if I choose one that other people didn't choose, right, then that's kind of bad, right? And so you can still think of approval voting even when there's 1 winner. And so again, like this is implemented in MakerDAO. There can only be 1 winner, but you can approve of any number. There's no limit on the number of approvals you can make with this idea that like I'm kind of indifferent between these. Like I just can't distinguish them.
And so if you checked, are these rankings pretty robust over different?
We've tried over some
simulation?
sets. Yeah, I mean, so yeah, again, this we've had to choose, this plot here is there are 4 proposals that were uniformly distributed in 0, 1, and you had to, but it seems reasonable. We can't actually go up to big numbers because approval voting gets so complicated once you have a lot of proposals. The calculating the winning probability, if you have a lot of voters and a lot of proposals and everybody's voting for 2, and if you want to simulate whatever these are, I mean, it's not so bad. These are simulations, but it doesn't scale well for a lot of proposals, basically.
So, like in hindsight, is there an intuitive
reason
why you're seeing this?
I'm
What's
not sure.
driving the
This is I was
ranking?
trying to figure this out. I don't know why this is. I'm saying this is like pretty new. We're still thinking about this. I don't know why this is because I thought approval voting would be better. Right, like that was what I thought coming into this. And there's, here's where it is kind of better. If you're worried about like malicious takeover, this is another thing that like a lot of, the white papers will talk about is like how you imagine somebody's attacking your DAO or something, how much vote power do they have to get to do something bad? Yeah.
What's the difference between preferences and beliefs? Like, what's the difference between saying I have different preferences, I'm trying to get the maximum expected like utility versus just saying I have like different signals of one centralized quality parameter?
So in our model, every proposal has a true quality.
Yeah.
Okay, and you get some signal, you get some noisy signal, you get like a quality plus epsilon,
Yeah.
and every voter's payoff is increasing. For simplicity, think it is exactly the quality of the proposal that's elected. So if you elect the proposal with true quality Q, then every voter's payoff is Q. Right?
But I mean, voters make decisions based on their expected quality, which is S.
Yes. Yeah.
And so I guess like, how is that different than saying, okay, let's imagine everyone's utility, like actual utility, is drawn from the same distribution as S is drawn, and then you're like, instead of saying Q,
Yeah.
Q
Okay.
somebody,
Yeah. So you say your utility is,
comes from some distribution F. And then,
Yeah. So I don't know off the top of my head how that would change things.
Okay.
Sorry. We could talk about that. But yeah, I'm sorry. I don't know what that
That
would.
sounds good.
So the other thing we want to ask is, suppose you have some minority that wants to kind of tank your proposal and get you to choose the worst of the options, right? Like, how does your system handle against that? And here, approval voting does well. And initiative voting is kind of the worst. So this is, on the x-axis, is the percent of the vote that the malicious party controls. So here they control 10% of the vote. And you say here again, there's 4 proposals, and what's the chance that the adversary can get you to choose the worst of these proposals, right? The adversary wants to destroy things. And so if they have 10% of the vote and you're doing 2 approval voting, they never get you to choose the worst one. But if you're doing this initiative voting, actually like 20% of the time they get you to choose the worst of the proposals. And so this initiative voting is up here. The adversary has much more control once they, for these cryptographic parameters of, the adversary controls a third of something. If the adversary controls a third of the voting power, they can always get you to choose the bad proposal in the initiative voting. And they almost never can if you allow 2 approval voting, which is kind of interesting. And I think what's happening here is that basically voters are not that good. If their signal is bad, voters are not that good at distinguishing 2 proposals that are kind of close to each other. And because they get some distribution, and if 2 distributions are close, the voters can't distinguish them. And so in head-to-head voting and this initiative voting, right, the adversary can kind of push you a little bit to the bad one every time. So if the adversary controls 10% of the vote, it can kind of push you kind of 10% towards the bad one. And if 2 things were almost the same, they can push you to the worst one in the first vote. And then the second vote, they can push you a little bit more to the worst one. And every vote, they get to push you a little bit towards the worst one, basically. And in the continuous voting, where you get to see everything, 10% of the vote just isn't enough to get you towards this bad one. All the voters can see that this is the worst one, and none of the voters were voting for this worst one anyway. And so this kind of thing that the sequential voting allows the adversary to sequentially push you towards the bad outcome seems to give you this kind of lack of robustness.
Reuse its stake to attack every vote as opposed to just having a one shot.
I think that's the, and again, this approval voting helps you with this because, again, it kind of just puts all the votes towards the slightly better stuff. Like in 2, if you vote for 2 things, you just have tons of votes for the slightly better ones, and you're never going to let the adversary get you to the really worst one. So this is sort of where we are at this initial analysis of this, but they're interesting questions how much, if the adversary gets to introduce new proposals, what happens here? And we haven't thought about that too much. Just as a final wrap up, as mentioned before, we have a paper that is asking what happens if you allow people to directly vote on on a parameter. So this is a paper we called token-weighted crowdsourcing. I'm happy to talk about that later. There's other things, right? You can have ranked choice voting, and if you have ranked choice voting, that's not even a single thing, right? You have to say once people rank their votes, how do you actually choose the winner based on these rankings? And I haven't seen much in terms of how does ranked choice voting work as an information aggregation mechanism. Again, in this kind of model where people have poor information but sort of aligned preferences, how does ranked choice voting work? And how does it compare to these kind of things? I think that's a really interesting question that I'd be interested in exploring in the future. And then there's questions, if we have like a minute or two. Another kind of question in this space that I think is really interesting is like, for different types of systems, you might want to like really protect the minority stakeholders. So from like the original DAO, this is like a section from the original DAO white paper, which is like you have a community investment fund, and they were really worried of this thing. If you put in like 20% of the money to invest, and you have like no say in where it gets invested. And so a big chunk of the white paper and a big chunk of the like complexity of the system was to prevent against this majority robs minority attack, right? And so that notion of a DAO had this thing, if people vote to invest your money in something you don't like, you could fork off to choose a child DAO, right? Which then the fact that you could choose these child DAOs had a big effect in terms of how the whole like DAO fork played out. But right, this was all about this question of, you have a community investment fund, and if you have 5% of the stake or 10% of the stake, it's not like you get to choose 5% of the outcomes, right? You get zero choice, right? And so how do you ensure that people have like proportional representation? That if you're voting to invest in things, or if you have Gitcoin grants or something, right? If you put in 5% of the money, you should choose 5% of where things go. And so just looking around, there have been like really interesting proposals in the political science literature that I haven't had that much time to think about, but like I want people to think about in the blockchain space. So one of them is storable votes, which is, right, there's going to be sequential proposals. So every month we're going to allocate, $10,000 or $100,000 to various things. And if I choose to abstain this month, my vote carries over to next month. And so if I have 5% of the vote, maybe I could get closer to 5% of the money to allocate.
Stake weight is basically divided across your votes. You could just say, like, I can spend this much in budget.
Yeah. No, but I mean, it's not exactly the same, right? Because if I vote, it's still, it goes up, yeah.
So they own the system in that one final vote.
Yeah.
Seems problematic.
Another proposal that I found in the literature is this balance voting, which imagines like two-phase voting. So you have like a two-step thing where, so imagine like you want to add a collateral asset to Maker or something. In phase one, you get to choose yes or no, do we add the collateral? And then the people who get to vote in phase two are only the people who lost the vote in phase one. And so phase two might then set like the parameters around how you get to use this. There are obviously potentially issues around this, but like again, it's kind of an interesting type of model that both of these systems are designed to get at this thing that the DAO mechanism was like trying to do with its child DAOs, and would be, I think, pretty straightforward to deploy in the blockchain space. And so I think people should kind of be thinking about, I don't know, again, if these are exactly the best mechanisms, but there's an interesting question of if your goal is to protect minority stakeholders, like how should you do that? And so yeah, that's mostly what I wanted to share with you today. But I think there's like lots of open space in this blockchain voting system. Thanks.
Yeah, on those last 2 points about storable votes and balanced voting, are you aware of any real-world applications?
So I found a handful of papers, and these are links, and I can give you the slides. They've tried them, I think, in some lab experiments, and I don't remember if there were any. But
Crypto space.
in the crypto space, I've never seen anybody talk about this in the crypto space at all. But I just wanted to throw these out here more to just get people thinking of like, there's a lot of mechanisms that you could use. Like there's the space of like how you aggregate votes is just enormous, and depending on what you want, like you should think about these crazy mechanisms. Yeah.
So I was curious, do all of these basically assume the vote is completely synchronous, so you can't employ a strategy based on the votes that you can see other people have cast within that round?
Yeah, so in our model, all the votes are completely synchronous. Yeah, that's right. And that's also an interesting question, right? Is can you, yeah.
Yeah, well, that's definitely something we've been thinking about running tally privacy while elections are actually happening, so you can simulate the synchronicity. But yeah, I guess that's obviously one solution with crypto is just
to
simulate
hide
a synchronous.
Yeah.
I guess the other question is if there's any actual strategy proof. Well, I guess no election strategy proof, but is there anything that's better, or the strategies are more difficult, assuming that the election's not synchronous?
Yeah. I don't know the answer to that. I bet there is, right? It's, again, an interesting question, but we haven't looked at it. We just assume everything is synchronous. And sort of related to that, there's interesting questions about bribing voters, right? Reviewers on these papers, right, immediately ask about, like, once you can do this, right, you can ask about bribing voters, and blockchain is a great space for bribing voters. So there's a little bit of like cryptographic stuff you could do there, like even, which I think is like actually an interesting question about, even if you make the vote tally private using some like ZK mechanism, usually in most of those things, the voter still has the witness, so they can still effectively sell their vote. And so you want some kind of like deniable encryption kind of mechanism so that you couldn't effectively sell your vote. This is sort of like an interesting thing of, can you make that?
Okay, so I wanted to mention reality-aware social choice is a variant of social choice, which is could be a basis for Sybil resilience. I'm going to share in the chat, try to share in the chat a reference, yeah, which is relevant for approval voting and also parameter selection in the presence of Sybil voters. So just wanted to call your attention to that, another strand of research in this direction.
Great, thanks. Thanks.